Hello everyone, my name is Harsh Gandhi. I am a PhD student in Civil and Environmental Engineering at University of Massachusetts Lowell. Today, I am presenting the effect of various pile head displacement in pile designing of integrated abutment bridges. Integrated abutment bridge is the bridge without the expansion joint in compared with the conventional bridges. In conventional bridges, expansion joints are there to counteract the change in bridge length due to the temperature. States and municipalities have used integrated abutment bridges as an effective means of eliminating expansion joints. As construction and maintenance of expansion joints are costly, nowadays integrated abutment bridges are in demand. But in contrast, designing of integrated abutment bridges are complex due to the effect of thermal loading. Temperature is major concern in designing of integrated abutment bridges. In general, bridge decks are in connection with abutment wall, which is connected with the pile heads, either with pin or fixed connection. Hence, designing of pile are in direct relationship with the pile head displacement due to thermal loading. Pile head displacement are in proportion to temperature difference, span length of bridge, and steel thermal coefficient. In this study, main objective was to analyze the effect of range of span length on design of HP pile in integrated abutment bridges under thermal expansion. Important criteria in pile designing are fixity point, bending moment, and top and second segment length of HP pile. Fixity point is effective length of pile where displacement along length becomes 0 or near to 0. Bending moment is important aspect of pile designing to decide occurrence of plastic hinge in pile, and length of second pile segment is the length between points of zero moment here, where top segment is length above the first zero moment. To analyze the effect of different pile head displacement by using LPile software, 8 cases were studied by varying the pile head displacement ranged from 0.05 inches to 0.5 inches by keeping the thermal loading, soil profile around the pile, and cross-sectional properties of pile constant. By doing so, larger pile head displacement occurs due to the larger span length, in contrast with smaller pile head displacement due to the short span bridge. And major pile designing criteria were analyzed in both strong and weak axis pile orientation. Here, in pile modeling result of 8 cases, figure 2 represents the displacement along the length of HP 12/74 pile oriented in weak axis. The results are in good agreement with assumed hypothesis. As displacement at pile head increased, the effective length of fixity point was also increased. Here, in zoomed in image of near fixity point, we can observe clearly that the effective length of fixity point is higher in 0.1, 0.2, 0.5 inch of pile head displacement than 0.05 inch pile head displacement. Here, figure 3 illustrates the moment along the pile length of HP 12/74 pile oriented in weak axis. The moments result are also in good agreement with assumed hypothesis, as moment in top segment and second segments are increased with the increment of pile head displacement. This moment analysis is important to check in both top and second segment, as occurrence of plastic hinge in any segment can cause pile failure. Similarly, displacement and moment analysis of HP 12/74 pile oriented in strong axis was studied as shown in figure 4, and we can see pile oriented in strong axis also followed the assumed hypothesis. Now golden question is, which pile orientation is better, weak axis or strong axis? In table 1, quantitative analysis has been presented. We can observe that with the increment in pile head displacement, effective length of fixity point is also increasing by 0.5 feet in both weak and strong axis. However, pile oriented in weak axis will reach the fixity point earlier in comparison with the strong axis due to the flexibility of pile oriented in weak axis. That means in designing, we can decrease the pile length if it is oriented in weak axis by almost 4 feet in case of HP 12 by 74 pile. That was for the fixed point criteria. For unbraced length of top and second segment, the length in both segments are increasing almost by 0.25 feet with the doubling of pile head displacement in both weak and strong axis. And similar behavior is happening in maximum moments of HP 12 by 74 pile in both segments. Moment are increasing by almost 75% in top segment and by 87% in second segment with the increment of pile head displacement. However, we can see that moments for pile oriented in strong axis are higher than the weak axis. Means pile oriented in strong axis can have more moment, which make them safer in case of plastic hinge occurrence in compare with the weak axis. Quantitatively, for HP 12 by 74 pile, the increment in pile head displacement will decrease moment capacity in weak axis by 48% in top segment and by 50% in second segment. Hence, pile oriented in strong axis are better than the weak axis in pile designing aspect of moment. Hence, the governing question is, can we increase the pile size in weak axis to make them better for the moment aspect of pile designing, or by choosing the strong axis we can increase the pile length while designing. In a nutshell, both the pile orientation have leading designing advantage in particular aspect of pile designing, and range of breach span will also impact the fixity point, unbraced length of top and second segment, and moment in both segments significantly. Thank you for listening the presentation.